Thank you. So I'd like to start directly from the broader motivation of this work, which is simply to design a concurrent lambda calculus. So this means essentially a concurrent functional language, since the lambda calculus is the basis of all functional languages. And you might think, okay, that's easy, where's the big deal? You just take a functional language and you add communication channels. The problem is that you would like to have a language with very good properties, because the lambda calculus has a really rich mathematical theory and good properties, which actually allows to use it in practical settings. So the properties that we would like to have, for example, are that the calculus should have a carry-hour correspondence. We will see what is a carry-hour, but it means a type system, a natural type system. So that allows to reason about programs, because this is essential, especially for concurrency, where which is a style of programming prone to mistakes. And so we want to have this type system. Then we would like to have, for example, deadlock freedom. So the type system ensures statically that there are no problems in the communication structure that the programmer should have organized before. Then we would like the so-called strong normalization, so that all the programs that we write terminate, because this is assumed to be used as a programming language with some specification, and you would like to fulfill the specification. And then we would like to have finally confluence. So it doesn't matter how we evaluate the programs, you will always reach a unique result. And this is a basic property of lambda calculus. So we would like those properties to hold, and there were attempts in this direction, but I don't think there is something that fulfills all these requirements. And so let's see where to start. Well, a natural starting point is linear logic. The idea is that we will use logic since we would like to have a type system, so a logic. The idea is to let logic to determine a corresponding concurrent lambda calculus, which in this way will fit very well the logic. And it's known that starting from linear logic, you can get some process calculus. So there is this result of Kairos and Fanning, which tells us that propositions, logical proposition, can be seen as sessions. So in particular, there is a carry-hour correspondence, which says that sequent calculus proofs in linear logic can be seen as parallel processes. Then the process of cut elimination, so the process of removing lemmas from proofs, can be seen as synchronous communication between these processes. And then propositions can be seen as session types, exactly as those as we've seen in the last talk. So the calculus is the pi calculus, Milner's pi calculus, which have been discovered independently. And I revised the syntax because I will build on this. So there is the input construct. So if you have a process P, you can put before an input. So x, y means that the process reads an input on the channel x and then stores in the variable y. Then there is the output construct. So x bar y means that the process wants to make an output along the channel y, x, and transmit y, and then continues with b. Then there is the parallel construct, and then there is a construct for making channels private. So this is the pi calculus, and the basic reduction, computational reduction, is the synchronous communication. So the two processes have to be ready, one to transmit and the other to receive. If there is no synchronization, there is no communication. So in this example, the process on the left sends the Z on the channel X, and then the other process takes this message and stores it in the variable Y, as you can see. So this is the calculus, and there are some limitations in this setting. It works very well, but there are some limitations. So for example, this calculus doesn't match the full cut elimination process, while the asynchronous calculus does, but that's another thing. It's not the carry hour correspondent with Milner's calculus. And then for what interests us is there is no integration in the same system of functional and concurrent computation. And so you have to use either to use the calculus to program, which is not very helpful, or you have to expand the system and to add separately the functional part. And so you can do that. And there is no way of representing code mobility. So sometimes it's more efficient to send directly code on a communication channel instead of a pointer to it. And then the communication patterns are a bit more restricted than we will see in our calculus. For example, there are no cyclic communication patterns, so no direct way of representing cyclic schedulers, for example, like in Milner. So our solution doesn't have these limitations, so it's an improvement on this respect. So what is the result that I will talk about? Multiplicative linear logic can be seen as a concurrent lambda calculus, so a type system, a natural type system for a concurrent lambda calculus that we call lambda par. And so what is multiplicative linear logic? Well, if you know it, well, it's okay, you already know it. If you don't know it, it's just a subsystem of classical logic in which you have some restriction on the reasoning, but is more or less ordinary logic. So it's natural and it's very well studied. So the result is that we provide a proof system for the logic, which is a natural deduction with multiple conclusions. This system is very well known in logic, and it gives rise to programs of this calculus lambda par. Then there is a correspondence between normalization, which is the process of eliminating logical detours from proofs, with the computation in the calculus, so beta reduction of lambda calculus, and communication, which is added on top of the lambda calculus. And propositions are just types, so ordinary types, so arrow types, essentially, with also disjunction. So the syntax is essentially an extension, a simple extension of the lambda calculus, both of the lambda calculus and the pi calculus. So it's just a merge. And there is so the void, the terminated process, which is the circle. And then we have channels. So with the x bar u, I denote a channel with the continuation u. And it's an output channel. When this channel is applied to an argument, it will transmit along the argument along the channel. So then we also have channels without continuations, so output channels without continuation. Then we have parallel composition. Then, well, we have a construct for terminating processes. It's not very important. And then this is the communication part. Then we have the lambda calculus part, so the functional part. So we have variables like x, y, z, and so on. Then we have application of a function u to an argument v, as in all functional languages. And then we have the function definition, so lambda x u, which actually is syntactic sugar because it can be defined as a channel x with continuation that contains the channel. So in a sense, this is the lambda because it's self-communication in a sense, so local communication, which is what a lambda operator does. And then we adopt this syntax as in PyCalculus. So with x bar vu, we denote the application of the channel x dot u to an argument v. And this construct just sends v on the channel, along the channel x, so as you expect, and then continues with u. So exactly as in PyCalculus, that's why I use this notation. So we will see the reduction rules and an example in a moment, but first let's see the types. So the typing rules are of the following form. On the left, you have a variable declaration, as usual. So x1, xn are declared of type a1, an. And then on the right, you have the programs that you are constructing. So you have that T1 is of type B1, Tn of type Bn. And these are the programs that are intended to be executed in parallel. And the typing rule, the first typing rule is the one that introduces the parallel operator, so the concurrency. So if you have S that is of type A and T is of type B, then you can take the parallel composition S bar T of type A par B. So this connective par is just OR in linear logic, and so it has the expected rule. And then we have, the declaration of variable. If x is a variable of type A, then we can use x as with type A. Then there is the function application. So u is of type A implies B, and t is of type A. If you have this premise, you can apply the function u of type A implies B to the argument t of type A, as you expect. The real novelty, the main novelty, is that the rules for function definition, and so from the logical point of view, implication introduction. So there are two rules. So the first one is the one for building a function. So if you have that T is a program of type B, and actually you can see the side condition, which is that X occurs in T, then it means that T is a function of X because it contains X. And therefore, it makes sense that you conclude, if X is a variable of type A, you can conclude that lambda xt is a function from A to B. So this is the expected rule. But what if the variable X does not occur in T? Then we have the communication. So if the variable X is in delta, it means that you can communicate the argument of this term xt in delta. So the type of this construct is A arrow B. It means that it takes an argument of type A, transmits it along the channel X, and then continues with T, which is of type B. Okay. And then there is the typing rule for the empty process, the terminate process, which is false, is of type false because it does nothing. So, there is an example. And then the reduction rules are these ones. So, first you have the beta reduction. So the application of a function to an argument, lambda x ut, can be rewritten as utx. T replaces x. And then you have asynchronous communication. And you can see C and D are two contexts. And if you find the term x us in one context, then you can transmit immediately the message u along the channel x, as you can see. And vice versa, if the term is on the right of the parallel process. So as an example, for example, you have this. On the left, you have x output x u, and you see that there is zx on the right. So this lambda term can receive the argument, and so this reduces in one step to circle lambda yy zu. So the process has received u. So there is a call by value version of this calculus, and the interesting part, so you can only transmit values. The interesting part is that with this call by value calculus, you can represent synchronous communication. So it's easy to check that if you you can define the synchronous, the blocking input and the blocking output, and then you have you force the processes to synchronize. So this is a feature of the calculus. Then, well, one of the main results is, as wished, that every typed term that contains an output is not normal. So there is a progress. This means that this is deadlock freedom. If a process wants to transmit something, then it will transmit at some point the message. And the other result is the calculus is fully confluent. So every typed term, so type the term, has only one normal form, as wished. So this is the theoretical result. Then I think that this calculus can encode the session type, the PyCalculus of Keres and Fanning. I didn't prove it, but I think that it holds, it's future work. And it is possible to extend this calculus, which is a linear lambda calculus, because we are in linear logic, to a full typed lambda calculus. I think it's possible to do that. So, thank you.
Thank you. I was wondering whether you can comment on the relationship of your work with the work by Bernardo Tonino, Luis Kerr, and Frank Penning, ESOP 2013. They basically integrate a contextual monad representing a process language, a session type language, into a functional language. Mm-hmm. I was just wondering.
Yeah. So the difference with the calculus is that we have a single logic, so which is multiplicative linear logic, mm-hmm. that is able to represent at the same time both the functional and the PyCalculus part. In their case, they have essentially two logical deduction systems which are put together by a monadic construct. In this work, we wanted to have a straightforward type system that is able to represent both the features.
Okay, thank you.
So a quick remark on this initial slide where you mentioned all the limitations of the PyCalculus. I'm sure if Robin Miller would be here, he would contradict all that, because
they are not the limitation of the PyCalculus, but of the type system used for the PyCalculus.
All right, I got it wrong. And so there is many years ago, Gérard Boudol had this blue calculus. Yeah, it wasn't a.
Sorry, what?
Gérard Boudol, he had this blue calculus 20 or 30 years ago. Mm-hmm. Not sure you're familiar with that. Mm-hmm. It was an attempt to bring together the lambda calculus and the PyCalculus, mm-hmm. and I think the language was a little. It was simpler than the one one you have here. I'm not quite sure how it works with types, but are you aware of this work?
Yeah. As I said, it's difficult to have a single calculus that has many good properties. And for example, I think in that case, that calculus lacks a logical type system as we used. And so it's not clear then how to, if that calculus can have a confluence property, because there is no type system. And so this is, I think, that was the main limitation of that work.
There's a question at the back.
First of all, that was really cool. Thanks. And so I have two questions. One is, so Jennifer Pagan and Steve Zdanzovic had a paper where they linearized Perigos's lambda mu calculus, and they showed that it's basically Wadler's classical process calculus, more or less, like up to some polarization. So do you know how your work compares, like in this space, between that calculus, Wadler's, etc.? And my second question is, do you have like plans to extend to the additive fragment as well?
Okay, so yeah, I know that work, and I think that more or less the same result should work for this calculus. So this calculus should have a close correspondence, can be translated in mu calculus. Mm-hmm. It's not at all easy to work out this translation, but I think it should work. With not the same technique that they have used, another technique, but still should work. And then, so sorry, what was the other question? Hmm? Yes. Well, what I would like to do is to have a full typed lambda calculus in this system. So first to extend it with a bit of exponentials. Then it makes sense also, yes, to add some additive operators. So it makes sense. But first, at least I have in mind to add a bit of exponentials.
Thank you.
So, related with Stephanie's question, I have worked to encode, fully abstractly encode Frank-Fenning's calculus with polymorphism with system F, and there is a mapping from pi calculus to Frank-Fenning's pi calculus to system F to pi calculus, and we extend it to also process monad. So I'm happy if you can look at the relationship, because we have all properties, of course, system F, so we have all properties you declared at the beginning with a higher order. Mm-hmm. And ESOP 2017 paper.